Hello, this is Dr. Brown. In this short video, we're going to do a quick review of periodic functions, which you've already talked a good bit about, and show some practical examples of why these periodic functions are so important and play an important role in our lives. Now, we've already talked about trig functions, sine of t, cosine of t, tangent of t, and also cotangent of t. And in looking at the graphs of the sine function, we all know that it always starts out at 0, goes up to a peak, goes down to a negative peak, and comes back to 0 again, and it does that in a period of 2 pi. So every 2 pi, the function repeats. Now the cosine function also has a period of 2 pi, but it always starts out at its peak and then goes down to a negative peak of -1, then comes back up to the peak again, and now you see a period of 2 pi, and it repeats forever and ever. So remember, sine and cosine functions both have a period of 2 pi. Now, when it comes to the cotangent function, you remember that the cotangent, actually the tangent function, is equal to y over x equals sine of t over cosine of t. So anytime cosine of t goes to 0, there's going to be a vertical asymptote in the tangent function. And the same goes for the cotangent function, which is cosine over sine. So now, as we graph this, we see one thing, that the period is 2 pi. I'm sorry, is pi. It's not 2 pi. So for tangent and cotangent, the period is pi. You will see, for instance, the tangent is 0 at t equals 0. It has a full cycle and goes back to pi. At pi, it goes back to y equals 0. This continues on and on. So remember, the period of tangent and cotangent are both pi. Now, just looking at the sine function just a little more carefully, y equal f of t is equal to sine of t. If we are at a peak of 1 at pi over 2, if we go to 5 pi over 2, which is 2 pi over, we get back to the peak. Also at t equal a, we have f of a, and in a time period of 2 pi, it gets back to f of a, and the period here is 2 pi. So we can say for the sine function that f of a is equal to f of a plus the period. In other words, it will repeat itself, which is f of a plus 2 pi. And also, if we go an integer number of 2 pi's, it'll still be the same function. So f of a plus 2 pi equals f of a equals f of a plus 2k pi. So it repeats in 2 pi, 4 pi, 6 pi, 8 pi. And in general, if a function is periodic, f of a equal f of a plus t, is equal to alpha of a plus k times t, where k is an integer. So for the tangent function, the period, of course, is going to be pi. But for sine and cosine, it's going to be 2 pi. Now let's look at the general sinusoidal functions and understand what we call the amplitude and period of sinusoidal functions. Here alpha of t is equal to a constant a times the sine of omega t. Omega is a constant, and a is a constant. And this particular function will have a different period, which we'll see the equation for in a moment, and it's got an amplitude that's the absolute value of a. Now we also have g of t is equal to a cosine of omega t plus phi. This phi is also a constant, and it basically causes the waveform to be shifted to the right or the left, depending on how big phi is. We're going to look at that also in a moment. But anyway, we define the amplitude as being the absolute value of a. The period is 2 pi divided by the absolute value of omega. In most cases, omega is going to be positive, but it could be a negative number, and you still need to be able to get the period. As an example, determine the amplitude and period of y equal f of t is equal to 8 minus 8 sine of pi t. The amplitude is the absolute value of minus 8 equal 8, and the period is 2 pi over omega, which is pi, which is 2. So this repeats every 2 units. Now, look at some practical examples of sine waves and cosine waves. You have to look no further than your dorm room or your home, and you will see a socket where you plug in appliances and so forth, and the waveform might be v of t equal 170 sine of 120 pi t. In other words, the voltage coming out of there can reach a peak of 170 volts, which could be very lethal if you get your hands wet. So be careful. Anyway, the waveform looks like 170 sine of 120 pi t. If we graph it, we see that the amplitude is equal to 170. And the period, t, is equal to 2 pi over 120 pi. Omega is 120 pi. This equals 1/60. And since t is in seconds, the period is 1/60 of a second. And so the waveform goes from 0 up to a peak of 170, down through 0, then back down to minus 170 and back to 0. It's called alternating current, which means it goes positive and negative. If you look at a graph of the function over a period of 1 second, you're going to see 60 cycles. Sometimes we call it 60 hertz. Now, let's look at one last example of a practical use of a sinusoid. Your satellite data coming to your home if you have a satellite dish, and the data coming from your cell phone through the cellular system are high-frequency signals. Now, going to your satellite dish, you might see something like S of t equal 10 sine of 25 billion pi times t. Now, this is a very high frequency signal, and this is what it takes to get your TV programs carried on this waveform. And the period is 2 pi over 25 billion pi. It's 8 times 10 to the minus 11th, which, if you graph one period, you get one period in 8 billionths of a second. Now, for your cellular system, the period is going to be a little bit longer. The frequency of the satellite is 1 over the period, which is omega over 2 pi, which happens to be 12,500,000 hertz, which is 12.5 gigahertz. Now, your cellular system is about 2 gigahertz. The last item I want to cover is going to include phase shift. We want to find the amplitude, period, and phase shift of a sine or cosine function. And we have a function here. The current in a circuit is 120 sine of 10 pi t minus pi over 6. We want to know what the period is. The period is 2 pi over omega, which is 10 pi, is equal to 1/5. The amplitude is 120. And the phase shift, we're going to have to factor 10 pi out of the sine argument to see what the phase shift is. So we factor 10 pi out, and we get t minus pi over 6 divided by 10 pi. Notice that this is still the same as this. We just factored 10 pi out so that we could see what the phase shift is. And pi over 6 divided by 10 pi is equal to 1/60th. So we get 120 sine of 10 pi times t minus 1/60th. So the phase shift is 1/60th to the right. Notice if this is negative, the phase shift is to the right. If it's positive, the phase shift is to the left. Now, to choose the correct graph below, we first of all notice that this is a sine wave that's going to be shifted just a little bit, 1/60th. So first of all, we eliminate the cosine waves, and then look at the shift, and the only one that works here is the third one, where the shift is 1/60th. Notice that the period, which we know is 1/5, is correct on this graph. Taking 13/60th minus 1/60th, which is the distance between 2 points where the value is 0, we get 12/60 equal 1/5, which is what we expected. So that is a short video on periodic functions and their practical applications. Good luck on the test.